Welcome everyone back to Physics 220i. This is a lecture that kind of sort of corresponds to class day of Friday, August 28th. As always, there'll be interactive work that you should do as you watch this video, and that will be due on our next class period, which I think of as Tuesday. So there'll be interactive work as part of this video related to the topics here: displacement, time interval, and motion diagrams. And you should watch the video and upload your interactive work before Tuesday night. And then there'll also be, in addition, a homework assignment that is due at the same time. I always like to start with just a silly, fun, sometimes relevant, sometimes not, nerdy comic. So there's our Venn diagram funness in the lower right there. Okay, let's talk about some physics. Our goal is to describe motion this semester, and one fundamental idea related to motion is position, where an object is and how it's moved. So when objects move, we can think of their initial position and final position. To begin with, we're just going to think about one-dimensional motion, so motion along a number line. Or another way to think of it is like in a 100-meter dash or a 200-meter dash, where it's like a straight line, or running along a football field, like that sort of motion, where the side-to-side motion is not interesting. It's only progression along one direction. So we have initial position and final position, which have the obvious meanings. And then displacement, which we represent typically with a delta x. That triangle is the Greek letter delta, and we usually have it mean a change. So in this case, the difference between the final and initial position. Okay, these are typically in standard units measured in meters, although it can be measured in yards or inches or furlongs or parsecs or whatever. We're typically going to use meters, and then all the variations on meter, like centimeter and millimeter and kilometer and whatnot. Okay, so it's very important for you to have a visual physical intuition about what the distinctions are between initial and final position and displacement. And one way to develop that intuition is by drawing, making a picture that shows us what each quantity represents. So final position tells you where something is, initial position tells you where something is, displacement is something different. It tells you how far it moves. Okay, so our first interactive work for the day. Imagine a running back. This is American football. A running back runs from the 10-yard line to the 15-yard line for a gain of 5 yards. Draw a picture that includes the running back and represents all three numbers, and label everything appropriately. Okay, so this is yards, not meters, because football. But I want you to make a drawing, and I'll show you the answer in just a moment. But just as a reminder, the way I want you to do interactive work in this class is I want you to have a physical piece of paper right now and write down your answer. Sometimes I'll ask you to give a short explanation. In this case, I want a drawing. You don't need a short explanation. You don't need words. At the end of this video, you're going to have multiple interactive things. I want you to take a picture and then scan it or convert it into a PDF, and then upload that file under the submission for this lecture. So that's going to be your interactive work. And as I said in the first video, the goal here is to practice the ideas early and often. Learning physics is doing physics. It is not memorizing definitions. That is, to be honest, not very useful. It's doing. So think of it as a musical instrument or a sport. You have to learn those chords or learn the motion of a good swing or whatever. So the interactive work will not be graded on correctness. I really want you to practice early and often, and that means making mistakes. So I'm going to show you the answer to this, but practice before you look at my answer. I'll give you pauses, that is, I'll tell you to pause the video and finish your answer. My intention here is many of these are at the couple minute level. Like, try it. And if you get stuck, it's okay to move on. But like, sometimes even getting stuck helps you understand the meaning of the answer more thoroughly. So, back to the problem. A running back runs from the 10 to the 15-yard line for a gain of 5 yards. I want each of those numbers, 10 yard, 15 yard, 5 yards, all marked with appropriate variables in your drawing. I'll pause here when you're finished, and then I'll continue. You should pause. 3, 2, 1. Okay. This is my version of the answer. So I have a running back. I didn't draw the football, but it's a standard stick figure, and 10 yards indicates the initial position. So x1 is a good way to represent that, and that's the position that the running back begins the process. The running back ends at the 15-yard line, so I'll mark that as x2, and we associate that with where the running back is at the end of the play. And then 5 yards represents the displacement, how far the running back goes. Couple things to note, of course, everything has units. Variables are put right where the 10 or 15 or 5 yards is appropriate. I use delta x to represent the displacement. It represents how far the running back goes. That's an arrow. So there's an arrow pointing to, in this case, where the running back ends. So any 5-yard gain could be represented by that delta x arrow. So delta x doesn't represent where it starts, doesn't represent where the running back ends. It's a 5-yard gain. Okay, let's move on. We can also define a similar idea for time. It's called time interval, and then there's the initial and final time, and we take a difference between those. I want to introduce then the third useful idea for our beginning discussion of motion, which is average velocity, which measures how quickly something is moving. And mathematically, it's the division of the displacement, delta x, and the time interval, delta y. There's a lot of subtlety in that definition, and we're going to develop that as a tool extensively. I'll put an example or two as a pencast on Brightspace. That is that lecture where I do example problems and you can see handwriting with my voice synced. So I'll put that up and label it as associated with homework 2. But for now, I want to move on and continue to talk about some other tools regarding motion. Okay, so imagine here's an image of a snowboarder going over a hill, and in the air. The way this photo was taken is that an image was captured roughly every 1/10 of a second and then superimposed on each other. So it's kind of a neat photo, but one thing I want you to notice is that the images of the person are quite close together in the upper left, and then they're actually quite far apart in the lower right. And the reason for that difference is that the person is moving faster in the lower right and they're moving slower in the upper left. So I want to develop a tool to help us think about behavior like that. This is a more cartoon version where we have a car and it's moving at a constant speed. And if we created, so that's represented in the separate images on the left, we could imagine doing something like the snowboarder image where we superimpose those images on each other, and that's the image on the right. I want to describe how, or in this case, the car is moving at a steady pace, and so the interval between each car in the image on the right is equal. So that's an indication that the motion is steady. Okay, so we're going to be describing all sorts of motion and drawing things like cars. Well, I mean, if I had to draw that with my hand, it would take a while. So instead, we're going to simplify things a bit instead of having you draw a car over and over and over again, I'm going to have you draw dots. And this is what I mean when I say a motion diagram. that I want you to think of some reference point on the car. You can like the headlights or the tire or the middle of the car or the bumper, but choose some reference point and draw as a dot where the bumper is at equally spaced time intervals. So every 1/10 of a second, draw a dot to represent where the bumper is. So this is what you see here is a car coming to a stop, and at the top and at the bottom there are dots that represent the bumper of the car at those equally spaced time intervals. And because, say, it's every 1/10 of a second, it doesn't have to be, but let's say it's every 1/10 of a second, those dots are getting closer together. That tells us the car is moving less distance every time interval. So as time progresses, the displacement between those dots is shrinking. Okay. We can attach numbers to these. So those dots we can put into a coordinate system. And for calculations, we'll generally do that. Oftentimes, we'll have like all the numbers. We'll start with 0 on the left and have it increasing to the right. And we can also attach time to each dot. Remember, the dots are equally spaced in time. So the dots here in the lower diagram represent every second the position of someone running a 50-meter race, which is, I don't think, a real race. So the dots always represent equal time intervals. And the reason why that's useful to do is that we can then use the distance between the dots to compare whether the person is moving fast or slow, whether the velocity is changing, that sort of thing. Okay, another interactive work. Plot the motion diagram of a car that begins at a stop sign, then drives through the intersection. So, I really want you to visualize this in your mind. Imagine yourself in a car at a stop sign, your foot moves to the gas pedal, presses the gas pedal, and you move through the intersection. I want you to imagine the motion diagram, that is the dots, that represent your motion from being at the stop sign and then moving through the intersection. So I'm giving you a choice here. You can choose A, B, C, and oftentimes when we have multiple choice options, I'll always provide E as a I'm lost option. You can do that, but spend a few minutes trying to think through. It is okay to put the wrong answer on your interactive work that you upload. I'll discuss the answer on the next slide. So, but pause here and spend spend a couple minutes thinking through the answer before listening to the next slide. 3, 2, 1. The answer is B. So the idea here is you're at the stop sign, and as you press on the gas, initially your car is moving slowly, and so it doesn't cover a lot of distance every 1/10 of a second. And so the dots will be somewhat close together. And then as you move through the intersection, you cover more and more distance, and so the dots will get farther and farther apart. The other options, A and C, don't describe that process. They describe something else. Okay, so let's stop there. I want to remind you that the interactive work, you should take pictures and upload. There'll be homework related to this, and there's a pencast for more numerical, for help in thinking about this in a more numerical way. But why don't we stop there?